Hello class, this is Fire Service Hydraulics and Water Supply, Chapter 6, Calculating Required Fire Flows. There are three main learning objectives we're going to cover in this chapter, and then we'll start with learning objective 1 that you see here on this slide. We will learn to differentiate among the three common methods used to determine the RFF, which is required fire flow. So RFF, remember that term, for manual firefighting operations. The first learning objective will be to explain the three common methods used to determine the RFF for manual fire operations. Secondly, we will, in learning objective 2, explain the two methods used to determine the requirements of fire flow for automatic sprinkler systems. And third, explain how fire flow requirement for the three classes of standpipe systems works. RFF is the amount of water that must be applied to the fire to control and or extinguish it in a reasonable amount of time. Determining the RFF has several benefits. It is important to compare the available fire flow to the RFF to determine if the water distribution system can supply the necessary amount of water should a major fire occur in the target hazard. It is also helpful in deciding which apparatus and personnel need to respond to a fire at the target hazard. Fire service personnel should be acquainted with at least one method to determine the RFF for a given occupancy. Three methods or formulas that are commonly used for the fire service in the last 60 years are the Iowa State formula, the National Fire Academy formula, and the Insurance Services on Office formula, or ISO formula. Now, it's important to note that these are based on the U.S. system of measurements, the imperial system, so they cannot be easily converted for use with the metric system. And we'll deal with that a little bit later in the chapter. In the first part of the 20th century, manual firefighting efforts were limited mostly to exterior fire attacks that used straight or solid stream nozzle. Interior fire attacks also relied on solid streams for applying water to the fire. There was no such thing as a fog nozzle. So they had to use straight line fire, try to shoot at the base after they cooled it down from the top, and it took a lot longer to put the fire out, but we'll talk about all of that. Development of the fog nozzle started in the mid-1920s, actually, with Captain Glenn Griswold, who looked for a better way to extinguish oil fires. Now, he correctly theorized that if water could be broken into little drops and then discharged across the fire, it would absorb the heat and dilute the burning gases, which he was correct. And he experimented with several different designs of fog nozzles. Griswold ended up settling on an impinging stream design that created optimally small droplets of water at pressures between 50 to 275 psi, which is 350 to 1925 kilopascals. He secured numerous patents and founded the Fog Nozzle Company to ultimately produce these nozzles, and he produced several models of them. He also produced applicator pipes up to 30 feet or 10 meters long that could be used to insert the stream in otherwise unreachable areas. Early Navy fog nozzles were equipped with an applicator pipe that could be inserted through an opening into a fire area. This was part of the Iowa State Formula U.S. Coast Guard and Navy experiments. One of the problems that they had was, particularly the Coast Guard and the Navy, if there was a fire on board a ship, sometimes you couldn't get access to the area where the fire was, or you needed to put it down before you could enter it. And having this kind of fog nozzle that could reach from a distance when you've got a blazing hot bulkhead in front of you made a huge difference. And so the experiment ultimately was a success, and we'll talk about the piercing nozzle, which we still use today. The U.S. Coast Guard and Navy experiments started 20 years after Griswold developed the fog nozzle, and the Navy and Coast Guard began these experiments, as I mentioned, using fog stream technology for interior fire attacks within confined spaces, as I explained. The initial research concerned containing oil fires within lower levels of ships. There was a gentleman named Lloyd Lehman who conducted the Coast Guard research that involved inserting fog streams via applicator pipes into completely closed rooms containing oil fires. He noted that immediately after the flow of water started, a massive amount of smoke exited the exhaust opening, followed by a mixture of smoke and then steam. This was soon followed by condensed steam, and within minutes there was no discharge whatsoever. He called this the indirect attack method of fighting fires. Now, Lehman's theory was based on the atmospheric displacement of the heat and products of combustion by the expanding steam within the space. And Griswold's direct attack theory was based on the dilution of the heat and combustion products. Both were correct based on the conditions of their test. So actually, between the two of them, all of those things happen when you subject a fog nozzle, an extended fog nozzle, into a confined space like that. Everything that each of the two of them observed ultimately ended up being exactly what happens. Lehman ended up refining his fundamental principles of attacking and extinguishing interior fires to include the indirect method that will work only in confined spaces containing significant involvement of fire, but it doesn't work well on an incipient fire. The fog stream should be played on the upper portions of the involved space. Firefighters should not be in the space in which a fog will be introduced, and furthermore should be protected from any steam as developed. The stream should be discharged into the fire area without interruption until the condensed steam that emerges has decreased considerably. Because when you place that fog spray onto a fire, even if it's in an enclosed space, as you heard, or just learned, that steam and smoke exit the area rapidly through any exhaust opening. And when that water expands into steam, it creates an immediate, what's called a steam flash, and it will burn firefighters to death instantly. So you need to make sure that they're not in the space where the fog's introduced, but at a safe distance. There was another gentleman you need to know about. This was Chief Edward McAniff, who was chief of the fire department of New York at one point, and he conducted tests under virtually the same conditions as Lehman and generally got the same results. He felt that the practical application of this method of fire attack would be limited to rare instances when perfect conditions for its use existed, but at the time he saw little or no application for the technique in standard structural firefighting. But in 1950, an exploratory committee validated Lehman's theories. So even though this was 25 years after these experiments began, there was continuous experimentation and validation from different incidents that his theories were being validated finally in 1950. There are two men, Floyd W. Bill Nelson and Keith Royer, who engaged in a continual set of experimental fires at Iowa State University, designed to explore all aspects of the fire problem. They developed the Iowa State rate of flow formula, and this formula was very practical because it enabled firefighters to calculate the RFF for any structure before a fire occurred. So you start to see the connection between fire inspections and getting to know your area of response prior to anything happening, so that when you roll up on a building, there's a pre-incident plan in place. Their formula was based on two fundamental principles. The first is 1 gallon or 4 liters of water will produce with a margin of safety 200 cubic feet or 5.7 meters of steam. 1 gallon, their second principle was that 1 gallon or 4 liters of water will absorb with a margin of safety all of the heat that can be produced with the oxygen available in 200 cubic feet or 5.7 cubic liters of normal air. Following these two principles, cubic area in feet divided by 200 equals the gallons of water required for control of a specific area involved in a fire. So here's the equation in U.S. customary or imperial method. You take the gallons needed, and that equals the volume of the room in cubic feet divided by 200 cubic feet per gallon. So it's very simple. Now, this equation is not a rate of flow formula. It only gives the total number of gallons or liters of water needed to control a fire in a given area. So it's not rate of flow, it's just total number of gallons needed. So here's an example of the application of the formula that was derived from the Iowa State research. Now, before I begin, just to remind you, to get cubic feet of an area, you take length times width times height. It doesn't matter what order you do that in, and they actually have it in width times length times height, but I'll get to that in just a second. So using equation 6.1, determine how many gallons of water would be required to extinguish a fire in a room that is 20 feet wide, 30 feet long, and 10 feet high. So in this case, they have gallons equals width times length times height, doesn't matter, divided by the 200 cubic feet you get per gallon of water. So gallons equals 6,000 divided by 200, so you need 30 gallons to extinguish a fire in a room that is 20 by 30 by 10, or 6,000 cubic feet. Now, Nelson and Royer derived the 200 cubic feet, which is 1.425 cubic meters of steam figure, from the expansion ratio of water to steam at 212 Fahrenheit, which is 100 degrees centigrade. And that expansion ratio is 1 to 1700. It's immense. Because 1 cubic foot of water contains 7.48 gallons, therefore, you take 1700 cubic feet divided by 7.48 gallons per cubic foot equals 227 cubic feet of steam per gallon of water. It's an absolute immense expansion. And to give you an idea of how immense that steam explosion can become, at Chernobyl, when reactor 4 melted down, they were very concerned about and it would have done it had they not taken heroic efforts. The core was melting through the cement pad that the reactor was sitting on, and underneath that was a fresh water source, as well as water that had been built up from trying to extinguish the graphite fire. All that was built up under the reactor. So they were in a race to put an extra concrete pad underneath the melting reactor core, because if it had hit that steam at the temperature that it was, it would have been an instant catastrophic steam explosion, and we would have had all of the radiation from all of the nuclear material from reactor 4 plus 3, 2, and 1, which were already there, plus all the spent fuel, and it would have made that material go critical and produced an explosion in the megaton range. So that gives you an idea of what steam has the power to do, and its instant expansion is so great that it can produce very catastrophic results. Nelson and Royer based the number 200 in principle 2 on tests that were determined to result that 1 cubic foot of pure oxygen combined with ordinary fuel produces 535 BTUs. Air contains 21% oxygen, and flame production stops when the oxygen level falls below 15%. So 21% oxygen minus 14% oxygen level equals 7% of air. Only 7% of air is available for heat production. Then multiplying this number by BTUs produced by a cubic foot of pure oxygen gives 535 BTUs, or 0.07% of air, which is 37 BTUs. This is the number of BTUs produced by 1 cubic foot of air. Because 1 gallon of water expands to more than 200 cubic feet of steam, 37 BTUs times 200 cubic feet equals 7,400 BTUs. So 1 gallon of water converted to 200 cubic feet of steam absorbs 9,330 BTUs. Because 7,400 is less than 9,330, They concluded that 1 gallon of water can absorb all of the heat produced by 200 cubic feet of air. Nelson and Royer also determined that 30 seconds was the maximum time required for effective use of the adjustable fog nozzle. They changed their original formula into a rate of flow formula, RFF. So here's the equation in U.S. customary or imperial number system. The RFF equals the volume of the room in cubic feet divided by 100. Given that the rate of flow is, or RFF, is the required fire flow in gallons per minute, and 100 is the cubic feet of steam created by 1/2 gallon of water. Paul Grimwood adopted the Iowa State formula for use in the metric system. Now, in the metric system, the RFF equals the volume of the room in cubic meters divided by 1.5. So the given values are that RFF equals the required fire flow in liters per minute, and 1.5 is the cubic liters of steam created by 1 liter of water. So here's an example. Using equation 6.2 for US, determine the RFF for a detached garage that measures 30 feet by 60 feet by 14 high. So the RFF equals length times width times height, or as they did it here, width times length times height, 30 times 60 times 14, divided by 100. That gives you an RFF of 25,200 divided by 100. So the RFF is 252. In metric, using equation 6.2, the metric, determine the RFF for a detached garage that is 10 meters by 20 meters by 5 meters high. So the RFF is 10 meters times 20 meters times 5 meters divided by 1.5 liters. The RFF then is 1,000 divided by 1.5, so the RFF is 667 liters per minute. The Iowa State formula remains widely used throughout the fire service. There is no scientific evidence to suggest that it is not still relevant. By the mid-1980s, the NFA was promoting a newer, simpler formula that quickly gained wide acceptance. And the NFA is a unit within the USFA that provides advanced fire service, managerial, administrative, and educational programs for career and volunteer firefighters, and also for fire officers. It offers both courses at Emmetsburg and local delivery courses throughout the United States, Emmetsburg being their home. The National Fire Academy flow formula was developed as a quick calculation, quote-unquote, formula that can be used as a tactical tool to determine fire flow requirements at the scene of an incident. It is intended to provide a starting point for deciding the amount of water required, the type of apparatus needed to deliver that water, and the number of engine companies that should be used to apply it. So their quick calculation formula is as follows. Length times width divided by 3 equals fire flow in gallons per minute for one floor at 100% involvement. So it's pretty simple and very straightforward. It is quick. So length is length of the structure in feet, width is width of the structure in feet. Note that this formula utilizes the area or square footage of the structure involved, unlike the Iowa State formula, which is based on the volume of the structure or room. So here's an example. Using this equation we just learned, 6.3, determine the fire flow formula necessary to control a fire that fully involves one floor of a 4-story structure that measures 50 feet long by 30 feet wide. So you take length times width divided by 3 equals the fire flow in gallons per minute for one floor at 100% involvement. Well, in our example, we have one floor of fully percent involved. So we take our length, 50 feet, times our width, 30 feet divided by 3 because we only have one floor involved. And that gives you the fire flow in gallons per minute at 100% single floor involvement. So that comes out to 1,500 square feet divided by 3, and that gives you the fire flow. And when you work out your fraction here, it gives you 500 gallons per minute of fire flow in gallons per minute for one floor at 100% involvement. So you need to pump 500 gallons per minute. Whether that takes more than one engine is what's decided immediately. But remember, one thing to keep in mind is potential for other floors to become involved. So that has to be considered as well. If more than one floor is involved in a fire, the fire flow is simply adjusted by multiplying the number of floors involved by the required fire flow for each floor. The NFA advises that the formula is considered reliable if only 4 floors or fewer are on fire. So if you've got something that's 10 stories high that's fully involved, this formula doesn't apply. The NFA formula also may be used to determine the RFF if only a portion of a floor is involved in a fire. The fire officer must use the square footage of the floor and the percentage of the floor that is involved in the fire. So here's an example of that. To determine the required fire flows, if a single-story structure measuring 60 by 40 is 75, 50, and 25% involved in fire. So you take your length times width, 60 times 40 divided by 3 gives you the standard fire flow in gallons per minute for the whole floor at 100% involvement. So work out your fraction, which is 2,500 square feet divided by 3. That gives you 800 gallons per minute of fire flow for 100% involvement. Well, if you want to know what 75% of that is, because 75% is involved, you take 0.75 times 800 gallons per minute gives you 600 gallons per minute. 50%, that's easy. That's 800 divided by 2, or 800 times 0.5, which is 400 gallons per minute. And 25% is 0.25 times 800 gallons per minute gives you 200 gallons per minute. So that's pretty straightforward. If the original fire building is exposed and it has exposed adjacent structures to fire, a 25% exposure charge of the required fire flow should be added for each side of the fire building with exposures. Should any exposures become involved with fire, that exposure should then be treated as a separate fire. So, and here's an example. Suppose that the structure in the above example has the one we just did, has exposures on 2 sides. Calculate the total fire flow necessary to extinguish the fire and protect the exposures. Now, we're going to say that this example has 100% involvement. So the required fire flow is going to be 800 gallons per minute. And the exposure protection is 800 gallons per minute times 25% times 2 exposures. So 25% of 800 times 2 is 400 gallons per minute. So total fire flow required for your fully involved floor plus the 2 exposures is 800 gallons per minute plus 400 gallons per minute. It gives you 1,200 gallons per minute. This is very simple and straightforward. In buildings of fire-resistant construction, if other floors are not yet involved but are threatened by the possible extension of fire, then those floors should be considered an exposure, and 25% of the required fire flow for the fire floor should be added for exposure protection for each floor above the fire up to 4 floors. Remember, that's our limit to use this particular formula. When using the NFA formula to determine required fire flows, it is important to remember that the answers provided are approximations of the amount of water needed to control the fire. Now, they're based on an estimation of the area of the building and the amount of fire involvement within the building. It's never been validated by definitive scientific or practical testing. Part of the reason for that is because while the simple mathematic principles may be the same, every fire is different. So you've got a different combination of materials, and then you have variables like contents. Some might be toxic, some might be explosive, some might be oxidizers. etc. So you've got a million variables, and that makes it impossible to validate it 100% scientifically, because the number of combinations in any given fire are infinitesimal. So this formula does provide firefighters and fire office with a starting point, and that's why I mentioned how many variables there can be. That's your starting point. You may ultimately find you need twice as much water because of something that is housed in that particular building, etc. So this formula provides firefighters and fire officers with a starting point to determine how much water they may need for an effective attack in normal situations. But as I mentioned, if unforeseen factors prevent control from being achieved within a reasonable time, the amount of water being applied may have to be increased. ISO evaluates many facets of risk, including occupancies or facilities. ISO. It looks at community fire protection, the entire community, and individual occupancies or facilities. The ISO formula is applicable to all structures other than 1 and 2 family dwellings that do not exceed 2 stories, and it is more involved than the Iowa State or NFA formulas, and is very impractical when you're actually on scene. So it's limited to pre-incident planning functions, but it is considered the most reliable of the 3. So pre-incident planning becomes very important because you've got that, and then you arrive on scene and do your quick calculation, and hopefully they'll be in the same vein. But this ISO formula being more accurate, you're more educated going into the scene of an incident because pre-incident planning has been done using this formula, and we're going to explain it. Now we're going to explain the ISO RFF formula. It's pretty basic, just like all the others. But remember, this one is a little more precise, so it's used in pre-incident training. So the formula is F equals 18C times A to the power of 0.5. Given the following values, F is the required fire flow for the given occupancy in gallons per minute, which we just learned how to calculate. 18 is a constant extrapolated during the research to develop the formula. So that's a reflection of physics. So 18 is your, it's called a variable constant, and that sounds oxymoronical, but it isn't. It is a variation that occurs, but at a constant rate. So that's what a variable constant is. And in this case, the constant is 18. C is the coefficient related to the type of construction for the occupancy in question, and A is the floor area in square feet. The construction types for the coefficient, which is C in the formula, following the construction classifications, are found in most building codes. Buildings that have or provide a higher fire load receive a higher coefficient. This results in a higher calculated fire flow than for a building of the same size but with more fire resistant construction types. So you can see where the precision of this formula would not work in the field, because you don't always know exactly what construction type you have if you just were to roll up on a fire and the building's engaged. However, because this one's used in pre-incident planning, you're seeing the building and its materials prior to an incident, so this formula can be applied, and the coefficient figures. So the coefficients for the formula are as follows. For wood frame construction, the coefficient is 1.5. These are the values assigned. Ordinary construction is 1.0. Heavy timber construction is 0.9. Non-combustible construction is 0.8. And fire resistive construction is 0.6. And what you can see is the higher the fire resistive capability of the construction, the lower the coefficient. For types of construction and or materials that do not fall squarely within one of these categories, planners can interpolate a coefficient that more accurately reflects the conditions found in said building. The interpolation must be limited to occupancies that are listed consecutively in the above list. In the ISO formula, area, which is A, is the building's total floor area, including all stories, but excluding basements. ISO recommends the calculated fire flow be rounded to the nearest 250 gallons per minute or 1,000 liters per minute if the flow is less than 2,500 gallons per minute or 10,000 liters per minute. 500 gallons per minute or 2,000 liters per minute if the flow is greater than 2,500 gallons per minute or 10,000 liters per minute. So here's an example using U.S. customary or imperial measurement in using and this is formula that we just reviewed, the ISO formula. So using the ISO formula, determine the required fire flow for a 3-story heavy timber construction mill that measures 75 by 200 feet. So you have F equals 18, which is your constant, times your coefficient, times your area to the 0.5 power. So F equals 18, your constant, times 0.9, which for heavy mill construction is, or heavy timber construction, the coefficient is 0.9 from the table a couple of slides back. And then your area, which is 75 feet by 200 feet, and you have that times 3 stories. So 75 times 200 times 3 stories raised to the power of 0.5. So if you work out the math, you have 18 times 0.9 times 45,000 to the exponent of 0.5. And when you calculate that out, the final answer is 3,437 gallons per minute, which you can round up to 3,500 gallons per minute. The ISO formula may be applied to any type or size of structure with the following stipulations. The minimum fire flow plan for any structure should be at least 500 gallons per minute or 2,000 liters per minute. And the maximum fire flow, depending on the type of structure, it should be 6,000 gallons per minute, which is 24,000 liters per minute, or 8,000 gallons per minute, which is 32 liters per minute. And again, that depends on the type of structure. The fire flow figures calculated using the basic ISO formula may have to be adjusted to, and I mentioned this before, on scene, you're looking at fire, FFR, and it might be twice what you initially calculate because of variations that are present in an individual scene. Well, it figures certainly into pre-planning as well. So fire flow figures calculated using the basic ISO formula, which is used during pre-planning, may have to be adjusted due to the level of fire hazard, as I mentioned, the presence of sprinkler protection, and exposures. If these factors are applied, the maximum fire flow may be increased to 12,000 gallons per minute or 48,000 liters per minute. Let's talk about fire hazards as they relate to the ISO formula. Basic fire flow may be reduced up to 25% for low fire hazard occupancies or increased up to 25% for high fire hazard occupancies. There are 2 ways to determine whether a structure falls into the low or high hazard categories, and we'll review that on the next slide. So the basic fire flow, as we mentioned, can be reduced or raised 25% in either direction for high or low fire hazard occupancies. So if you look at table 6.1, which is in your book, you see the ISO occupancy classifications on the right side of this slide. So you see a list of low hazard occupancies and high hazard occupancies. Then you need to also apply one of the occupancy combustibility factors. The evaluator has some latitude in applying one of the occupancy combustibility classes to the contents of the structure being evaluated. And you see these listed on table 6.2 right here. This is ISO occupancy factor. So let's do an example with this. In evaluating this structure described in the previous example on page 108, the inspector determines the structure is used to store bundled newspapers awaiting recycled. That is determined to be a free-burning combustibility class. If you go back and look at your tables, you'll see that. So you need to adjust the required fire flow appropriately. So you have fire flow or flow, which is F, adjusted, equals, and the reason it's going to be equal, you'll see in just a minute, or the reason it's adjusted is what you're going to see in a minute. You have 3,500 gallons per minute times, which, or 1,400 or 14,000 liters per minute, either one, times the occupancy factor. So if you take the fire flow value that you got from before, what you're doing here is adjusting it. So in the case of a bundled newspaper recycling storage facility, you have 3,500 gallons per minute, or for metric, 14,000 liters per minute, and you multiply that times a factor of 1.15. That gives you a flow adjusted rate of 4,025 gallons per minute, or 4,000 gallons per minute because you're rounding to the nearest zero. That is 16,000 liters per minute. So what we did was we worked the formula out before, and then we realized that, hey man, wait a minute, this is not a regular building, it stores a recycled newspaper, so we're going to have to adjust our flow based on the type of occupancy this is. So that's all we did, was we took our final value from before of 3,500 gallons per minute, we multiplied it times the occupancy factor from the table that's in your book, and that gave us a new gallons per minute for flow. Now let's talk about reductions, because we talked about increasing it because of a particular hazard, but you also have things that can reduce fire hazard. So automatic sprinkler reductions are the most commonly applied fire flow that have been determined by the basic formula and then adjusted for the fire hazard of the contents. Adjusted fire flow can be reduced up to 50% for complete automatic sprinkler protection. So for any building that is either fire resistive or non-combustible construction and has a low fire hazard, the sprinkler reduction may be as much as 75%. That reduction will depend on the extent to which the sprinkler system is judged to reduce the possibility of fires spreading within and beyond the immediate fire area that they cover and need to cover. So just because you can take a reduction for sprinkler or protection inside the building, you can also take a reduction for exposure separation. So you want to give credit for exposure separation, and this is most commonly applied fire flows that are determined by the basic formula and then adjusted for the fire hazard of the contents, as I just said. A percentage should be added to the adjusted fire flow for structures exposed within 150 feet or 45 meters of the fire area under construction. So if it's beyond 150 feet or 45 meters, you're going to give an adjustment towards less fire flow. If they're within 45 meters or 150 feet, you're going to add to the amount of total that you're going to need for fire flow. So this percentage will depend on height, area, and construction of the exposed buildings, the separation, as I just mentioned, and openings in the exposed buildings, the length of exposure, the provision of automatic sprinklers and or outside sprinklers in the exposed buildings, which is not uncommon, occupancy of the exposed buildings or building, and then effects of hillside location on possible spread of fire. So here's a table. It was just 6.3 from your book, chapter 6, obviously. This is the ISO exposure protection factor. So you can see the closer it is, the more flow you're going to need, because it's going to increase that percentage need by 25%, versus the bottom of the table, which says that 101 to 150 feet, you're going to only add 5% of fire flow need. And you got that as insurance, because at that distance, depending on the time factor it would take to engage the building, it's still going to most likely, if you can get to the main fire in time, not going to, it's going to, the possibility of it being involved is going to be tremendously reduced. But you want that extra 5% just in case you need it. So the total percentage will be the sum of the percentages for all sides, but shall not exceed 75% of the fire flow. So what we determined for is established fire flow, and then we said that you may have to increase it by as much as 75% depending on various factors, which we covered in 2 tables. So that being exposure and sprinkler protection. But, you know, of course, there are other variables too, type of construction, which goes in your basic formula, etc. So you start to see why this is more precise, but it would be awfully time consuming at the site of a fire, which is why this formula is used in pre-planning. So let's do an example based on the basic formula we got before, plus percentages up and down. So the total percentage shall be, in this example, the sum of percentages for all sides, but shall not exceed 75% of the fire flow. Well, that's the basic rule. So in our example here, the structure described in the example on page 109 that we covered has exposures on 2 sides. Both are approximately 50 feet away or 15 meters away. So determine the additional fire flow required to protect the exposures. So if you recall from table 6.3, and you can look at it in your book, an exposure that is 50 feet or 15 meters from the fire building requires an additional 15% per side. So if we take flow with exposures, sub-exposures right here, so we can figure exactly what we're looking at. That equals 4,000 gallons per minute, which was our basic total from above, or from previously, plus 2, which is 2 exposures, and times 0.15, which is 15% per side, and there's 2 of them, times your 4,000 gallons per minute. So if you take 4,000 gallons per minute plus the additional 1,200 gallons per minute for the 2 exposures, that gives you 5,200 gallons per minute. Pretty simple. So for a metric, for exposures you have 16,000. If you recall, we did this, you can do this exercise in metric as well. 4,000 gallons is 16,000 liters per minute. But the principle is the same. So if you take 16,000 liters per minute plus 2 exposures times 15% times 16,000 liters per minute, and you work out the math, your total is 20,800 liters per minute, adjusted to include the 2 exposures. The ISO lists other adjustments or considerations that may be applied to the calculated fire flow. The formula is not expected necessarily to provide adequate values for things as intensely fuel laden like lumber yards, petroleum storage, refineries, grain elevators, and large chemical plants, but may indicate a minimum value for these hazards. Judgment must be used for business, industrial, and other occupancies that are not specifically mentioned in the tables themselves. So, excuse me, for pre-incident planning, if it's a refinery, obviously, that's not listed in the table. So special considerations will have to be made. And all of that is part of pre-incident planning. So again, you can see why the ISO formula is much more precise, why it's involved in pre-incident planning, but is really not helpful on the fire ground, except for the fact that prior to answering a call to a particular location, there should be a pre-incident plan in place, and that will have an ISO total for you. And you can measure that against what you need at the scene, because there might be additional hazards that have been introduced to a particular scene that weren't in the pre-incident plan where the ISO number was calculated. So that's another reason why you have to have the ability to calculate on scene quickly. The configuration of the building or buildings and its or their accessibility to the fire department should be considered. wood frame structures also that are present and separated by less than 10 feet or 3 meters shall be considered one single fire area. Normally, an unpierced party or common wall may warrant up to a 10% exposure change. Now, if a building is exposed within 150 feet or 45 meters, there's normally some percentage increase for the exposure that will be made. When there are wood shingle roofs, they could contribute up to spreading fires and add as much as 5,000 gallons per minute or 2,000 liters per minute. Any non-combustible building is considered to warrant a 0.8 coefficient. ISO recommends using the specific fire flows for groupings of one and small two-family dwellings not exceeding 2 stories in height. Other residential buildings, the basic formula and appropriate adjustments should be used. If the residences are continuous, like a row of row houses or townhouses, a minimum fire flow of 2,500 gallons per minute or 10,000 liters per minute is recommended. But if they are small one-family and small two-family dwellings not exceeding 2 stories in height, as you see here on table 6.4, then it gives you suggested fire flow with exposure distance. So review questions. One question is, and remember these will be on quizzes and tests, name the 3 most common formulas for determining the fire flows for manual firefighting operations. That will be on page 94 of your manual. Next question, what theory did Captain Glenn Griswold base his development of the fog nozzle on? That will be on page 95 in your text. Next question, describe the difference between Lehman's indirect attack theory and Griswold's direct attack theory. That will be on page 96 of your text. And next question, why did Nelson and Royer feel the development of the Iowa State rate of flow calculation was highly practical? And that will be reviewed on page 97 of your text. Next question, which fire flow formula was developed in the 1980s as a quote-unquote quick calculation formula that can be used as a tactical tool to determine fire flow requirements at the scene of an incident? That will be on page 100 in your text. And next question, what purpose does the ICO or ISO serve? That will be on page 103 of your text. Two more questions. Which RFF formula is considered the most reliable of the 3? Considering we just reviewed it, you should get that. That's on page 103 of your text. And finally, what are some factors that require adjusting the fire flow calculations when using the basic ISO formula? That will be on page 105 of your text. 2 more questions. List 4 other types of adjustments or considerations that may be applied to the calculated fire flow. That is 108 of your text. And according to ISO or ISO, what types of dwellings should not rely on the basic fire flow formula? That will be on pages 108 and 109 of your text. Now, learning objective 2, we will discuss the 2 methods used to determine the requirements of fire flow for automatic sprinkler systems. Records kept by the NFPA, National Fire Protection Association, indicate 5 or fewer activated sprinklers extinguish more than 90% of all fires in sprinklered buildings, each sprinkler flowing at a rate of about 8 to 15 gallons per minute, and they are significantly more efficient and less damaging than larger cluster arrays of sprinklers. The required flow rate will vary for each system based on a variety of factors, including the types of sprinkler system, the building's construction type and occupancy hazards, the size of protected area, and numerous other factors. The required flow rates for automatic sprinkler systems include only the amount of water the system is designed to flow on its own. However, NFPA 13, Standard 13, recognizes 2 methods of designing automatic sprinkler systems, the pipe schedule method or the hydraulic calculation method. For pipe schedule system technique, this is an older, more traditional approach and involves sizing the pipe based upon the number of sprinklers supplied. NFPA 13 or Standard 13 limits new sprinkler systems being designed by the pipe schedule method to occupancies of less than 5,000 square feet or 465 square meters. It may be used to modify or expand existing pipe schedule systems. With pipe schedule systems, there's a tendency to use larger pipe than hydraulically designed systems, making them less economical in many instances. The water supply requirements are left substantially to the judgment of designers. And the table here that you see is table 6.5 in your text, water supply requirements for pipe schedule sprinkler systems. So you can see the occupancy hazard, which is light hazard or ordinary hazard, and the acceptable flow at the base of the riser, duration it should last, etc. So familiarize yourself with this table. NFPA 13 allows designers to exercise some judgment based on building size, ceiling height, construction type, and other factors that affect the quantity of fuel available. Now the differences between that and hydraulically designed systems is that hydraulically designed systems are widely used and use mathematical calculations to determine the required piping sizes and other design factors. It is currently the only acceptable method of designing protection for special and extra hazards. So the piping system does not apply to, for instance, a facility where you have oxygen stored in canisters. There are numerous benefits to the hydraulically designed system, including hydraulic calculations typically show that system performance will be acceptable despite using smaller pipe sizes. And also smaller pipes and their fittings and equipment reduce material and labor costs. And there are other types of pipes such as thin wall piping, copper tubing, and plastic piping that can be utilized, and all of these cause less friction loss. Most hydraulically designed systems are designed using computer programs. Then this involves the process of determining the required fire flow for a hydraulically calculated system. It's not simple, and that's why we use computers to help us design these specific hydraulically designed systems, or individual hydraulically designed systems for different facilities. In a hydraulically designed system, the required fire flow will be determined during the design process and revolves around many variables, as we mentioned, such as the occupancy class, size of the sprinkler system, the sprinkler discharge, design density, the size of the design area, and then other factors. Here's a review question. What type of extinguishing system is more efficient than manual firefighting because it detects fire in its early stage and extinguishes it with less water? That will be on page 109 of your text. Here's two more review questions. What is the primary advantage of using the pipe schedule method for designing an automatic sprinkler system? That will be on page 110 of your text. And next question, what are some of the benefits of hydraulically calculated automatic sprinkler systems? That will be on page 111 of your text. Now, learning objective 3, we will describe the fire flow requirements for the 3 classes of standpipe systems. Most modern standpipe systems are connected to a water supply system, obviously. The fire department may have to supplement water by pumping water from a fire hydrant or some other source. So for instance, if you have a building that has standpipe but it's connected to a tank that's on top of the building, well, that may drain down faster than it can be refilled. So you may have to supplement it with a hydrant. If you have to boost it with pumping or a fire hydrant from another source or some other source, this will boost available pressure, excuse me, pressure and volume of the water at the attack location or locations. The NFPA identifies 3 classes of standpipe systems, each with different requirements for operation and water supply. You have Class 1, Class 2, and Class 3. Class 1 are systems designed specifically for fire department use, and it's equipped generally with 2.5-inch or 65mm discharges to which attack lines may be connected. The structure type equipped with a single Class 1 standpipe system is required to have a minimum available flow rate of 500 gallons per minute or 1,983 liters per minute without being boosted by a fire department pumper. The structure must be equipped with more than one Class 1 standpipe system. And a fire system must have an available flow of 500 gallons per minute or 1,983 liters per minute, and each additional standpipe must have available 250 gallons or 946 liters per minute, up to a maximum of 1,250 gallons per minute or 4,731 liters per minute. Buildings other than high rises, the NFPA Standard 14 permits the system's flow and pressure requirements to be supplied by a fire department pumper. These are buildings other than high rises that have a standpipe. With Class 2 standpipe systems, these are designed for use by building occupants to attack incipient fires. These have hose cabinets or reels with 1.5 inch or 38 millimeter hose pre-connected, and these are no longer allowed by many jurisdictions in new structures as they tend to encourage the occupants to fight the fire themselves rather than notify the fire department and evacuate the structure. Now, that's a new standard, but buildings built previous to the adoption of the new standard may have these in place. So it's another reason that pre-incident planning is so important. Something you need to bear in mind when reporting to a scene. With a Class 2 standpipe system, it requires a flow of only 100 gallons per minute or 378 liters per minute at a minimum of 65 psi or 448 kilopascals, with no increased requirement for multiple standpipes. It has a required pressure and flow that must be available independent of fire department pumping apparatus. A Class 3 standpipe system combines the elements of both Class 1 and Class 2 systems. The water supply requirements are identical to those for Class 1 systems. Some review questions. First, how do standpipe systems contribute to manual firefighting operations? See page 112 in your manual for the answer to that. And next question, where are Class 1 standpipes usually found in high-rise structures? That will be reviewed on page 112 of your text. Next two questions, why are Class 2 standpipe systems often not permitted in newer structures? That will be on page 113 of your text. And which class of standpipe shares identical water supply requirements with Class 1 systems? That will be on page 113 of your text. As always, class, should you have any questions, please contact your instructor. Thank you for your attention. We will meet again for Chapter 7.